So basically, let's just look at a first order differential equation. Basically, a first order differential equation can be written as this. It's basically some function of x and y. The interesting thing is sometimes the function of x and function of y could be separated, and other times it's not possible. And of course, as the name suggests, a separable first order differential equation is one where it is possible to break up the f of xy, this f of xy, into, for instance, let's say h of x, okay, g of y, sorry, okay. So when it's possible to separate out the two functions into hx and gy, and the ultimate goal then would be that you would have this situation where you have dy divided by gy equals hx into dx. So that's what a typical separable equation looks like. Not necessarily with the gy in the denominator, but I mean we can change that to some, say, other I of y dy equals h of x dx. So the point is that you can see that on this side you have just y and the differential of y, and here you have x and its differential. And the advantage of this, and the reason we want to do this, is so that we can go to this next step, which is integrate both sides. These are called separable differential equations, and when they are separable, we can actually go and, in fact, integrate the two sides. So basically, you're solving two integrals, combine the end result, and to get the solution to the differential equation. So here's an example to a separable differential equation. Whether it is or not, let's see if we can figure it out. Okay, here's an example. Y dash is equal to xy squared minus 2xy. So on the face of it, it doesn't necessarily look separable, but a little bit of playing around tells us that we can rewrite this as y dash is equal to x into y squared minus 2y, okay, which means that we end up with dy over y squared minus 2y equals x dx. So we've separated so this equation is in fact a separable differential equation. Integrate both sides next. So if we integrate both sides, we end up with here, basically this is going to be the integral of dy over into y minus 2. Okay, let's do that. So the left hand side can be simplified a little bit. Dy over y into y minus 2. And this side is quite straightforward. It's just going to be x squared over 2 plus constant c. Now on the left, of course, we can use partial fractions. So I will not show the details of this, but this can be written as 1 over 2 into y minus 2 minus 1 over 2y dy is equal to x squared over 2 plus c. So now we have, when we integrate this, f log of y minus 2 over y, okay, is equal to squared over 2 plus c. And then you end up with basically y minus 2 over y equals a e to the x squared. The 2 will go across, multiply both sides by 2. So the half will disappear from the x squared, and it will multiply into it will become a 2c, but raised to the exponential, you'll end up with this. So then we will continue to simplify that. So this can be written as y minus 2 is equal to ae x squared y, which we can write, I want to leave it here, so we can say y then is equal to ae x squared y plus 2. Bring the y's back and you end up with y is equal to 2 over 1 minus ae x squared. And that brings us to the end of this particular problem.